All right. All right, let's get started, everybody. I hope everybody had a good weekend. Um, we're going to get right into it. Just a real brief clarity on the schedule. We have our exam this evening, but the homework isn't due today. It's not due till Wednesday. I had a couple of people who went ahead and submitted it, and there's nothing wrong with that. But just to make sure everybody's clear, you do have a couple more days on that. We are going to have a homework today in steel due Wednesday for those of you in steel, but because of the exam, I made that homework incredibly short, and that'll become clear in steel design. Today, since we have our exam, we're going to do our exam review. Just a couple points on the overview. So I'm going to deliver it on Blackboard. For those of you that are in steel design, this is going to be the same deal as last week in terms of the logistics. The exam will open up today at 4 p.m. And it will close at 7 p.m. So you'll have a 3-hour window to do the exam. Keep in mind the exam is designed to be 50 minutes long, so it's not a long test, but you have an open window to do it. That does not mean I would start the exam at 6:50. I would start the exam, like at 4 or as close to 4 as you can, just to give yourself some time. And in case there are any technical hiccups and whatnot, you want to give yourself some time. But I did want to give you a little bit of wiggle room there. The exam's open notes, considering everybody here's at a distance. So you can use any resource that's on Blackboard. So the lecture notes, the homework solutions, or the lecture recordings, anything that's on Blackboard, fair game. You just can't give or receive aid from another person. That's pretty much the limit. And so yeah, one thing to keep in mind, some of my design methods are a little bit different than maybe what's in the textbook. I usually do that to ensure that you don't have to use as many aids, that you can just do it by hand. So that's just something to keep in mind. I copy and pasted this slide from Steel because the format's the exact same. 5 short answer conceptual questions, 3 computational problems. One thing I do want to be clear on, and everybody in Steel did a very good job of this. I didn't have anybody that didn't do this, but I want you to type out an answer for every question, even the computational problems, even the ones that you do calculations on. I want you to type out an answer. The way that the test will be set up on board, every answer can be answered by typing something in. And I want everybody to do that. And it really helps me with grading because I can look at the problem, and if the problem has the right answer, I can look at the math pretty quickly. And if you did the calculations correctly, I can grade it fast and move on. Everybody in steel design, the exam was on Monday, and I had the exam graded the next day. And so this was part of the reason why I was able to do that so quickly. So please type an answer out for every question. You will need to upload a PDF of your scanned calculation, so there'll be calculation-based problems. You can write out the short answer questions on there if you want on your scratch paper. You don't have to, as long as you type them in, that's fine. Some of you did that, I think, maybe just to ensure that I definitely got the answers, and that's fine. I don't have a problem with that. I put on here, CAM scanner's good, but you all can use whatever app or system that you want to scan this into a PDF. As for the topics on the exam, like I said, the exam's going to cover 3 topics. It's going to cover T-beams, doubly reinforced beams, and shear analysis and design. And what I have here for the topics, this is basically just what we did after exam 1. So with T-beams, make sure that you can compute MN and PMN for T-beams, and make sure you can design a T-beam. And by designing a T-beam, that means selecting the reinforcement pattern. Remember, T-beams are known cross-section problems. You don't have to proportion the T-beam. You just have to pick the reinforcement. Same thing with the doubly reinforced section. Not the same thing. I just want you to analyze doubly reinforced sections. I don't want you to be able to design them. We never covered design with doubly reinforced sections anyways. More often than not, it's not something you desperately have to do. So you just need to be able to determine phi mn and mn. So make sure that you can analyze a doubly reinforced section. And as for shear, which is the topic that we've done most recently, make sure that you understand shear in general. You can compute the capacity, and you can lay out stirrups and whatnot for beams according to their shear forces. The rest of the slideshow, I've got a lot of slides, but what I did is I went through all the example problems and I put all of the formulas that we sort of derived in class into these slides. I'll take a little bit of time to go through them. So first off, we have the analysis of T-beams. So the first thing that you have is if you have a T-beam in a floor system like you see below, you have to determine the effective flange width, so that B distance on the top of the T-beam. And so the effective flange width is, we have two formulas for whether or not you're dealing with T-beams in the interior or L-beams if the ones that are on the outside. It's just the minimum of those three quantities. Just make sure that you're cognizant of your units. Beam lengths tend to be in feet, but beam dimensions tend to be in inches. So just make sure that you're using constant units there. Remember, with T-beams, we have two different cases that we analyze. It's whether or not it's a rectangular T-beam or a true T-beam. And that's just a function of whether or not your stress block is completely inside the top flange or if it dips into the web a bit. So you compute your area in compression and you compare that against the area of the flange. If the area in compression is less than the area of the flange, then your stress block is rectangular and it's a rectangular T-beam. If your area of compression is greater than your flange area, then it's a true T-beam. And I've got the formulas below for the areas of each. Now, if you've got a rectangular T-beam, the analysis is really simple. It's just ASFY D minus A over 2 to get your moment capacity. And A is the area of the stress block. It's the same formula as before. The big thing with rectangular T-beams is your B is the effective flange width, B for the top flange. For true T-beams, the analysis becomes a little bit more involved because we have to determine a new A value. The formula is a little bit more involved, and then we compute a compressive force in the flange and a compressive force in the web. Now, if you look at this box here on the bottom left where it says note, the tensile force in the beam is always still ASFY, and when it's all said and done, C should equal T. So your compressive force in the flange plus your compressive force in the web has to equal T. So it's just a check to make sure that all your math is done correctly. And then finally, Mn is your compressive force in the flange times its moment arm plus the compressive force in the web times its moment arm. For both cases, don't forget we have to determine what phi is, and the way that you determine that is you look at your C value, A over beta 1. You then compute your strain in the steel, 0.003 D minus C over C, and then compare that against your limiting strain, which is the yielding strain plus 0.003. And if the strain in the steel is larger than the limit, then A, your beam meets ACI requirements, but B, it also means phi equals 0.9. Designing T-beams, these come straight from our previous notes. So the first thing we do is we compute MU, the factored moment. Sometimes it may be given to us. We had problems in class where MU was just given. Sometimes we have to compute it. Remember, we don't have to make any assumptions with MU because this is a known cross-section problem. So you don't need to assume the self-weight of the beam because you already know what the beam looks like. You do need to compute MN required. You have to assume that phi equals 0.9. And you have to assume a rectangular T-beam to begin. When you design a T-beam, you start off assuming that the beam is rectangular, and you compute the reinforcement ratio, assuming it's rectangular, and then using that reinforcement ratio in step 4, you back calculate, well, what would A be if I put that much reinforcement in the beam? And so step 3, you assume it's a rectangular T-beam. Step 4, you immediately test that assumption. So if it is a rectangular T-beam, then A will be less than or equal to H sub F. So the stress block depth will be less than the flange thickness, and you can just go on straight to step 5. If not, then that assumption was invalid, and it's a true T-beam, and you go to step 8. Now, step 5 is really simple. You just AS is rho BD, select a reinforcement pattern, analyze it. It's that simple. If it's a true T-beam, the analysis becomes a tad more involved. You have to split it up into your moment couple and your flange couple. So the first thing you do is you figure out the amount of steel required for the flange steel couple, and then the moment capacity of the flange steel couple. Then you say, well, if I know the capacity of the flange steel couple, I say, well, how much capacity in the web steel couple do I need in order to safely resist that load, and then figure out how much reinforcement you need there, and select a reinforcement pattern based off both, based off ASF plus ASW. Again, these steps are only required if it's a true T-beam. And again, this is no different than anything we had in our previous notes. I just everything all into one section. For doubly reinforced beams, I was actually able to fit everything onto one slide. And so here's a doubly reinforced beam. First thing I'll note is just make sure you're clear on your notation. Remember, everything regarding compression steel is going to have a prime associated with it. So AS prime is the area of the compressive steel reinforcement. D prime is the distance from the top of the beam to the compressive reinforcement, etc. When you're analyzing a doubly reinforced beam, the first thing that you do is you assume that the compression steel yields. So you assume that the strain is larger than the strain at yielding. You determine, well, what would A be? What would the depth of the stress block be if that were the case? What would C be if that were the case? And what would the strain in the steel be if that were the case? Now, if the compression steel yields, the problem's pretty simple. We just compute our compressive force in the steel, the compressive force in the compressive steel, the compressive force in the concrete, the tensile force in the steel, and you do that just to verify that C equals T, and then your moment capacity as follows. If the compressive steel does not yield, then all those gray formulas up top are invalid. They don't, or well, the epsilon sub Ty formula is fine, but all of the formulas is calculating your A and your C and all that, those are invalid. We now have to redo all of that. So we use this quadratic expression to figure out what C is, and once we get C, we calculate a new compressive force in the concrete, a new compressive force in the compressive steel, and a tensile force in the lower layer of steel. And again, doing this, C should equal T. And so that's why I have those formulas there, because regardless of what case that you're in, it's probably a good idea to test that C equals T. If C equals T, then you know you've done something correctly. Finally, MN. Again, plug and chug. Those two formulas are exactly the same. The only difference is the formula on the right, instead of A, I wrote beta 1C because I want, again, I want it to be crystal clear that you have to recalculate C. You can't use the old values from above. You have to redo that. Finally, for shear, we have, I just went ahead and threw the design procedure because the design procedure includes all the formulas for analysis, like for instance, the V sub C formula down below, 2 lambda BD squared of FC prime. We know our phi value is 0.75. Our first step is always to construct a shear diagram. We need to identify the 3 regions where shear is greater than phi VC is definitely where we need stirrups. Where the shear is between phi VC and half of phi VC, we basically should be using S max. And the region where VU is less than half of phi VC, we don't need any stirrups at all. The only other thing I'll point out before I move on is that that when you're trying to figure out where these regions are, remember it's not as simple always as just plugging and chugging into equations. We found that on our lab work assignment in here, the homework 6.2, where there were point loads on the beam, and it wasn't as simple as just, well, I'll just go and plug and chug. If you look at the shear diagram will tell you where those points are. So you just have to keep your eye open there a little bit. We then compute 2 S values for design. Remember, we always round those down to the nearest inch. So if you calculate 5.3, you don't round that up to 6 inches, you round it down to 5 inches. Okay, round down to the nearest inch. We have our required stirrup spacing at VU star, and then our maximum allowable stirrup spacing. We always compute those 2 values. S max 1 is the minimum of D over 2 of 24 inches, and S max 2 is calculated using that formula there. Now again, it's possible that S max is smaller than S required, and if that happens, just use S max. It just indicates that the beam doesn't have a lot of load on it. It's very lightly loaded. For the procedure for moving on, if you have 2 values of S required and S max, again, this is only valid if S required is smaller. So if you have like an S required of 4 inches and an S max of 10 inches or something like that, we have to determine where we can start using S max. We know we're going to use S required at the beginning, so where can we start using S max? So using that S max, we compute a VS and then a phi VN, and then we go back to the shear diagram and figure out where that is on the shear diagram. It should occur in regions 1 or 2, most likely in region 1, but it'll be in region 1, but hopefully like right before region 2. Lastly, we lay out the stirrups, and I think this is probably one of the parts where everybody seemed to understand what was, everybody did very well on this part. You might have had challenges finding the individual distances or the individual values, but the actual laying out part seems like everybody did very well on. Usually we place our first stirrup at either 2 inches from the support or like half of S required from the support. And so you'll place your first stirrup and then follow the pattern as seen here in this slide. And that's it. That is the content on the exam in terms of the formulas, in terms of the concepts. That is exam 2 in a nutshell. I'm going to give everybody a minute. If anybody has any questions, hopefully you came prepared with questions. I'll give you all a sec to type that out in the chat. Of course, I think I haven't restricted audio. If anybody wants to ask a question, you're more than welcome to do that as well. But I'll give you all a minute to start typing those out. Hopefully you came prepared with questions. Don't be shy. While you all are coming up with some questions, I want to show you something. Give me 1 second. Let me do this. All right. Everybody here, does everybody here see my my web browser? Okay, good. All right. If you go to new lecture notes and supplements, so this one right here. Okay. I'll show you what I did here. So I know this might seem like a lot, but it actually really isn't. I just wanted to try and make it as easy for you as possible. So first off, design aids and supplements. These are all the design aids from before, the shears, moments, and deflections, and the beam design aid. I will go ahead and tell you that I'm not going to make the structural analysis on this exam super rigorous. There might be like a point load somewhere, but that's about it. Nothing super complicated. When you look here for the lecture notes relevant to exam 2, here's what I have in here. I have all the homework solutions that relate to this exam. I have all the old lecture notes from before the break, and then all the lecture notes after the break that are relevant. And honestly, where it says lecture 33 exam 2 review, that contains all the formulas that are on the exam, so it's all in one place. The only other thing that might be a little outside what you would expect is lecture note 5 or handout 5, but that's the one that has like the beta 1 values and stuff like that. Most of that stuff I'll probably like I'm not going to try and test you on stuff from before, but I wanted to have everything all in one place so that you wouldn't have to go on an expedition trying to find stuff. Again, I know it looks like a lot. It really isn't, because again, everything would be in this exam 2 review slide. I'll give everybody a few minutes. I mean, I'll say this. I'll give everybody till about 10:25 or 10:30. But if there are no questions, I mean, I am fine with ending early and we can start steel at 11. But I do want to make sure, what is the comparison to make to tell if you are a true T-beam or a rectangular T-beam? Are you talking about during analysis or during design? Or either one? I mean, either one. Okay. Here's what I'll do. Give me 1 second. Figure the easiest way to do that is to refer to stuff that we did in class. So give me 1 second. Okay. Does everybody see example 9A? Okay. All right. So this was a problem that we did in class. This was an analysis problem. So the purpose of the problem was to determine just FEMN, just to do the calculations to determine the capacity. So if you look here, here's the T-beam. And part of the purpose of this exercise was to just do the just to go through the notation. So it had a flange height of 4 inches, D value, so D was 24. So that D was 24. I'm going to use my cursor to sort of highlight stuff. The girder spacing was 5 feet or 60 inches. I believe in the problem you were told it had a clear web spacing of 50 feet, so you had to figure out what that value was. The web width was 10 inches, and so the first thing you have to do is you have to figure out that slice of the segment that you can cut out to turn it into a T-beam. So you have to figure out that width, that effective flange width. And so to do that, first off, plug and chug. We take the minimum of L over 4, BW plus 16 times HF, or the girder spacing. Now, this is what I was saying, like, just be careful on your units because the beam length, this was a 30-foot long beam. So, again, this is 30 feet, but all of these dimensions here, like this one and this one, they're in inches. So you have to make sure that you're being consistent. Now, when it was all said and done, we had a minimum of these 3 quantities. So the minimum is obviously 60 inches. And then we get to right here. And this is sort of going to Victoria's question. So we need to determine the location of the neutral axis. And so that's what I mean by determining whether or not it's a rectangular T-beam or a true T-beam. And so it involves computing 2 values. It involves computing the area in compression and the area of the flange. Let's take each one of those one at a time. The area of the flange, that's simple. It's just B times H, just the total area. So this flange was 60 inches wide, 4 inches tall, so it has an area of 240 square inches. The area in compression, that's a little bit more involved. So remember, what you're trying to do is determine the depth of the stress block. And remember, the depth of the stress block, or the size of the stress block, I guess I should say, is that magic value such that compression equals tension. And so let's start off looking at this expression here. So compression equals tension. What's the tension? Well, we have tensile rebar in the bottom, so it's just the area of the steel times Fy. So that's the tensile force. The compressive force, remember, we always assume that the stress block has a uniform stress of 0.85 FC prime, and so we have to determine the area of that stress block. We don't know what shape it is, we just need to know the area. Now the area, I solve for this, so I just divide both sides by 0.85 FC prime, and I get that. So ASFY over 0.85 FC prime. So if you plug and chug, you get 105.88 square inches. Now Victoria asked, how do you tell whether or not it's a rectangular T-beam or a true T-beam? You compare these 2 values. So the flange area is 240 square inches. That's how big the flange is. but the area in compression is about 105.8, 106. So the question is, can I fit the stress block completely inside the flange? And the answer is yes, you can. It's going to look something like this image over here on the left. Like you can see that red hatched region, that's the stress block, and it can fit completely inside the flange. So because of that, what does the stress block look like? What does that red shading look like? It looks like a rectangle. So it's a rectangular T-beam. Now, if you go to a future example, go to 9B, here's example 9B. You do the exact same calculation. Oh, hold on. Although here you end up getting a different answer, or a different comparison. This is example 9B, again, trying to do an analysis and look at the two values. We have the area in compression. We do the same math. It ends up being 179.82 square inches, and then the area of the flange ends up being 120. So here it's a little different. The flange isn't big enough to completely contain the stress block. So if you look over here, the stress block has to go into the web a little bit. So if you look at that red hatched region, the stress block is a T shape. It's a true T-beam. That's because the stress block looks like a T. Okay, so that's how you determine the difference between whether or not it's a true T-beam or a rectangular T-beam from an analysis standpoint. From a design standpoint, it goes basically to right here. So I'm gonna hop back and forth for a second. So give me a second. So let me skip here. So for design, whether or not you're dealing with a rectangular T-beam or a true T-beam is determined in steps 3 and 4. So in design, you know, when you're designing the T-beam, you know what the T-beam looks like. Like, you know the physical dimensions of the beam. You just don't know whether to analyze it as a rectangular T-beam or a true T-beam. And you certainly don't know whether that's the case in design because you don't have any reinforcement. There's no rebar because you have to figure that out. So you start off by computing MU, and then you figure out how much, you know, MN required, the strength of the beam required, assuming phi equals 0.9. And then you get into the guts of your design. So you start off assuming it's a rectangular T-beam, okay? And that equation there on the bottom, if you look, that equation should be familiar. We've used that equation before. That was the reinforcement ratio equation that we used, assuming that the cross-section was a known cross-section, that you knew what the beam looked like. Well, that makes sense. I mean, it's a T-beam and we know what the beam looks like. That equation assumes that it's a rectangle. Okay, that's the reinforcement ratio equation if you're dealing with a rectangular beam. So we start off assuming it's a rectangular beam. And so if it's a rectangular beam, how much reinforcement do you need? And that's what we do in step 3. And in step 4, we immediately verify that assumption. We say, all right, what if we took that much reinforcement and put it in the beam? So step 3 tells us how much reinforcement we need in the beam if it's rectangular. Step 4 says, okay, let's put that much reinforcement in the beam and ask, is it rectangular or not? So we back calculate A, trying to verify that assumption. Now remember, what is A? A is the depth of the stress block. So if A is less than the thickness of the flange, it's rectangular. If it's greater than the thickness of the flange, then it's a true T-beam. And so that's how you figure it out in design. I know that was a little bit of a long-winded answer, but I wanted to make sure I was clear. Did that answer your question, Victoria? Good. Again, everybody, don't be shy. I mean, this is what we're here for. If you got questions, please. I wanna make sure I'm doing my best to address them. I'll give you all a few minutes. Again, fire away. Does the L beam you mentioned differ from the T beam other than B? No. The only thing that differs, that's the only thing that's different, is the formula for B. Every single thing else is completely the same. Everything. The analysis protocol, the design method, every step, nothing changes. Just that formula. And again, it's just because it's the beams on the outside. It doesn't change the fact that it is a beam with a flange on top of it. It's just the flange has different dimensions. Can you do a quick overview of example 13 in the notes? Here, give me 1 second. That was the, remind me, I'm looking at some notes from a couple years ago. That was the shear design problem with the distributed load. Am I correct? The one that we did before break. Okay. All right. So here's the example. These calcs are from a couple years ago, but the math really hasn't changed all that much. In fact, I don't really think it's changed at all. So we had a beam with a uniformly distributed load. It has 4 KSI concrete, 60 KSI steel. It's 16 inches wide, 25 inches effective depth. This beam had a lot of load on it. It had 11.5 kips per foot distributed load. So, I mean, that's a lot. That's 11,500 pounds every foot. It also was 20 foot long. Now, first thing that I have here in the slides, again, I wouldn't totally require you to do this. Excuse me. I wouldn't totally require you to do this on the exam, but this is something that should be within your abilities. So it's a distributed load, so the reactions are WL over 2. You cut a section, look to one, cut a section, look to the left. So you can see I cut a section right here, and then I look to the left. So if you cut a section and look to the left, that looks like this right here. And then if you sum forces vertically, what do you have? You have WL over 2 going up, and then what do you have going down? You have WX going down, and you have V going down. So WL over 2 going up, WX and V going down. And so this is your expression, solve for V, and here's what you get. And so this, so if I zoom out a bit, so this equation for shear and this equation right here are the exact same. It's just plugging the values in. So this is, WL over 2 is 115 kips, and then W was that. And so those are your two expressions for the shear diagram. In order to plot the shear diagram, so we can draw a quick and dirty one pretty easily, but we need 3 values for the plot. We need VU star, we need X at PVC, and we need X at half of PVC. And so PVC, 2 lambda BD square root of FC prime. Remember, square root of FC prime, you put in PSI, you get out PSI. And so this comes out to be about 51,000 pounds or 51 kips. PVC, 0.75 times that, and then half of PVC, take half of that. VU star, that's the VU at X equals D. So plug in D in the expression before. Don't forget to convert that to feet to make sure that your units are consistent. And then X at PVC and half of PVC respectively. So this is your shear diagram. you can see, we have this linear region, so you can see how it trails down like a line. That's just, your raw shear diagram. Remember, though, our shear diagram starts at VU star for design, so that was like 91 kips. We need, stirrups are required everywhere between the support and FVC. That's region 1. Region 2 goes to half of FVC, and region 3 is out to the end. So this is the region where we require stirrups. This is the region where we should be using S max, and this is no stirrups at all. Next, now I formatted my steps a little bit differently here, so bear with me. When I was doing the calcs a couple years ago, I went through and demonstrated how with more increments of stirrup spacing, you were able to decrease the number of stirrups. So you can sort of ignore this part here, this design 1. I won't make you do that in class. Really, for our purposes, what you need are 2 S values. You need an S value that's required at VU star, which ends up being 4 inches. Again, you compute 4.66. You round that down. Remember, whenever you compute an S value, you round it down, not up. Next, we need a maximum S value, so S max 1 and S max 2, plug and chug, and this is the S value that we get, which is 12.5 inches, but again, you round that down. So you have an S of 4 inches and an S of 12 inches. Next, you determine where you can start using S is 12 inches, so start off with VS. VS gives you 27.5 kips, assuming that S is 12 inches. FVN is 58.6 kips, and so where does that occur on the shear diagram? It occurs at around 4.91 feet or 58.9 inches. So what do? We place our first stirrup at X equals 2 inches. We use 4-inch spacing until we get to right here, and then we use 12-inch spacing. We get to half of FVC, and so that would be our answer. And that's really all I'm expecting of you for this exam and really for this class. The only thing that I do in class to improve on this is if you look at the example, we're really only using 2 increments. We're using 4 inches and we're using 12 inches. Well, what if I threw something in the middle like 6 inches? See how I've got 20 stirrups on the beam or 40 stirrups total? Well, instead of 40 stirrups total, maybe if I threw another increment in between, maybe I could reduce the number of stirrups. So what I did in class is I said, well, what if I tried S equals 6 inches? And so if I use S equals 6 inches, I repeat what I do in step 3, and I end up getting that value of 37.4. So I sort of do it again, and I'm able to shave off a couple stirrups. Again, to be absolutely crystal clear, I'm not going to make you all do that on the exam. I just want to show you that's what we did here. I'm going to be honest with you. I don't remember if we did this in class a couple weeks ago with canceling lectures. I don't know. I don't remember. So that's why when we came back after break, I said, let's just do another distributed load example to make sure that we're on the same page. Again, that right there is where I expect you to stop. Now, did I cover what you wanted, or was there anything specific? Why do we round down S values? Okay, great question. Why do we round down S values? The reason why we round down S values is because of this equation right here. Okay, so let's take a look at this equation. This equation tells you the shear capacity provided by the stirrups. Okay, so remember, how does a steel beam how does a reinforced concrete beam resist shear? Well, it resists shear 2 ways. The shear capacity provided by the concrete, the VC, the 2 lambda BD squared of FC prime, and then the capacity provided by the stirrups. I mean, that's why you're putting stirrups in the beam, is because you need stirrups because the concrete beam isn't enough. Now, here's the expression. How do you compute VS? All right, you take AV times FY times the quantity D divided by S. Okay, so S is on the denominator. Okay, so keep that in mind. Now, let's say you do some math and you find that a beam needs a stirrup spacing of 5.3 inches. Okay, so let's say that you compute S equals 5.3. If you round that up to S equals 6 inches, what happens here? Okay, If you have an S of 5.3 and you round it up to S equals 6 inches, what happens to your VS value? VS goes down, right? Higher denominator equals lower VS, which equals lower capacity. So the conservative thing to do, and what makes sense from a capacity, is to take that S value and round it down. That's one way of looking at it, is to look at the math, but let's also just look at the physics of it. Let's just look at the real life scenario. What you're computing when you design is S, how far apart those stirrups are, okay? So if you have a value that's like 5.3, rounding up would mean you're going to say, well, here's what I need for the stirrups, but I'm just going to make it larger. Well, that wouldn't make sense from a capacity standpoint. If you're trying to design and you have a choice, you're going to want to take those stirrups and pack them closer together, right? More closely spaced stirrups is going to lead to a stronger beam. So there's two ways of looking at it. One is just the equation. Again, if S goes up, VS goes down. So when rounding, you'd want to round down. But the second is just to look at the physics of the situation. Did that answer the question? If I was overly confusing, that's fine. I can retry it. Good. All right, we still got plenty of time. I want to make sure that everybody else is getting their money's worth. Again, I got to earn my paycheck, so if there's any questions, I want to answer them. Can we quickly review laying out stirrups? Are you talking about... Oh, my screen froze. Hold on. Are you talking about this part right here? Like assuming that this was correct, that this is what we needed? Like you can get to this part, and then it's like, okay, get from this part to this part. Let me try something. All right, so give me 1 second. While I'm getting ready for this, let me see if, again, I could walk and chew gum, so if you need me to answer another question. Hold on. Stop sharing. Okay, so you're talking about going from this to a layout, am I correct? And again, if you need to turn on your audio, that's fine. So let me show you how this works, okay? Now, hold on. Okay, so here's the beam, right? So we place our first stirrup at x equals 2, okay? So to be clear, at the support, this is x equals 0. And so what I'm going to do is I'm going to place my first stirrup here. So I've got my first stirrup, and that is at x equals 2, okay? Now what I'm going to do is I'm just going to start placing stirrups at 4 inches, Okay, so let me just sort of draw that out. 1, 2, 3, 6. Okay, all right. And I'll just draw a few of them to kind of explain. Okay, and just think of this like it's a graph, like you're graphing values. Okay, so this is x equals 2. So if I put my first stirrup down, again, I'm using 4-inch spacing. So if I'm at 2 inches and I go out 4 inches, that's x equals 6. And so this one's going to be x equals 6 plus 4, which is 10. This is x equals 14, x equals 18, x equals 22, x equals 26. Follow me so far? You follow me so far, Isaiah? Okay. All right. So let me put this sort of in a table so that we're clear on this. So using 4-inch spacing. Okay. So would you agree that the first stirrup got me to 6 inches? The second stirrup got me to 10 inches. Third got me to 14. 4 got me to 18. 5 got me to 22. 6 got me to 26. See what I'm doing? Now, remember, our goal is to get to 58.9. At least at or past 58.9. So we keep going. So 7 would get me to 30. 8 would get me to 34. 9, 38. 10, 42. 11, 46. 12 is 50. 13 is 54. 14 is 58. Now 14 isn't enough because we have to get past 58.9, so we need 15 to get us to 62. So that's why what we do is we say, okay, one stirrup at 2 inches is 2 inches, and then we said 15 at 4 inches is to 60. Okay, because 15 times 4 is 60. And we just do the same thing again with 12-inch spacing until we get to 100.2. So we said, so from here, we would use 4-inch or 12-inch spacing. So our first stirrup, if we're at 62 and we go to 12, that's 74. 2 was that 74 plus 12? What is that? 86. 3, 98, and then 4 gets us to 110 because we had to get to 100.2 inches. So that's why we do 4 at 12 inches is 48. Did that answer your question? Good. All right, I got time for maybe one more. If there's any questions in chat, we got time for another one. And then we got to hop on over to steel. Any more? I'll give you all a minute. Then we gotta move on to steel design. All right, last call for questions. All right, everybody. I think I'm going to go ahead and call it. I'll see most of you in Steel here in a little bit. For those of you not in Steel, again, the exam will open at 4 p.m. It will close at 7 p.m. Again, I would not start it at 6:50. I would start as close to 4 as you can, but that gives you plenty of time to go through the problems and upload your calcs. I'll be monitoring email and whatnot pretty fastidiously during that time in case anybody has any technical hiccups. But with that, I wish everybody the best of luck on the exam, and we will see you all on Wednesday. I will do my best to try and get the exam graded by then. At most, it will be Friday because I can't put it off too long or the grading will just add up. So that's all I have, everybody. We'll see you on Wednesday, and best of luck on the exam.